Artificial intelligence evokes images of sentient machines and digital brains. But beneath the marketing buzz, the mathematical reality of machine learning is entirely mechanical. It is an exercise in pure function approximation. To understand exactly how it works, we first have to look at the baseline it replaced. For over a century, computing relied on a strictly deterministic model, traditional software engineering. In this traditional model, a human programmer explicitly authors the logic. They write rigid if-then rules, feed in input data, and the processor calculates the predetermined answer. This architecture works flawlessly for calculating payroll or routing emails, but it fails when inputs become highly variable. You cannot hard-code rigid rules to reliably identify a human face across varying lighting conditions, different camera angles, and changing expressions. The logic is simply too complex for a human to write. To solve these probabilistic, real-world problems, computer science could no longer rely on human-authored rules. The computational architecture itself had to be inverted. This split-screen flowchart illustrates the inversion. Instead of feeding rules and data to get answers, machine learning feeds data and known answers into an algorithm to infer rules. This generated rule is strictly a mathematical formula. Generating that formula requires training. It is a mechanical process where algorithms act as function approximators. It ingests thousands of historical examples, constantly estimating the optimal mathematical parameters to minimize the error between its guesses and the known answers in the training dataset. The underlying mathematics driving this process trace back to mathematicians and neurophysiologists in the 1940s, who built physical circuits to model neural pathways. Modern deep learning is not magic. It's simply foundational mathematical optimization, scaled to massive proportions. To see exactly how this math works in practice, we can build a foundational predictive model from scratch. This scatter plot maps a continuous variable. Suppose we want to predict a person's annual income based solely on their height. The algorithm searches for a pattern in the historical data by attempting to fit a straight regression line through the center mass of the plotted points. That line represents a specific mathematical equation, y equals mx plus b. In this equation, m represents the slope of the line, and b is the y-intercept. In machine learning, these two variables are explicitly defined as the model's parameters. The algorithm's mechanical goal is to iteratively adjust the exact values of m and b until the measurable distance between the regression line and the actual data points reaches its absolute minimum. The model does not know anything about human sociology or corporate salary negotiations. It merely calculated that specific values for m and b produced the lowest error rate. It found a correlation, not a causation. To score the model's predictive power, data scientists use an evaluation function called R-squared. This metric measures how much of the variation in income can be mathematically explained by height alone. A high R-squared score on the training data is insufficient on its own. The model must be evaluated against reserved testing data it has never seen before, to prove it can actually generalize its math to new inputs. Calculating internal parameters to minimize an error function is the absolute baseline mechanic for all machine learning models, regardless of scale. While regression predicts continuous numbers, classification algorithms predict discrete categories. This map grid plots coordinates for a geographic classification problem, determining if a specific plot of land is vegetative or non-vegetative based entirely on latitude and longitude. When we introduce a new, unclassified coordinate to the dataset, the model requires a mechanical logic to assign it a category. The k-nearest neighbors algorithm, or KNN, classifies the new point based on the known labels of the data points spatially closest to it. The algorithm lets its search radius radiate outward until it captures a specified number of neighboring points. If the majority of those neighbors are non-vegetative, the new point is classified as non-vegetative. The k in KNN defines exactly how many neighbors the algorithm is instructed to check. This number is a hyperparameter. Parameters, like the slope in our linear regression, are internal values the machine learns during training. Hyperparameters are external rules the data scientist must manually set before training begins. Failing to rigorously tune these hyperparameters is a critical error. Software packages often mask them with default settings, inevitably leading to brittle models, making flawed predictions in production environments. Simple regression and k-nearest neighbors are highly interpretable, but they lack the capacity to solve high-dimensional problems like computer vision or natural language. In 1957, researchers developed the Mark I perceptron, the first major attempt to construct a network inspired by biological brain cell activity. Despite its ambition, the perceptron suffered from a severe architectural limitation. It contained only 2 layers, an input and an output. This drastically bottlenecked its processing power. In the 1980s, researchers realized that stacking multiple hidden layers between the input and output nodes exponentially increased the complexity of the problems the network could solve. This transition from flat 2-layer models to networks utilizing multiple hidden layers is the literal architectural definition of deep learning. This diagram shows how the math scales. Take the simple y equals mx plus b equation, encapsulate it into a single node, and multiply it into a grid. You now have the structural layout of a small neural network. The data flows systematically through this architecture, passing from the input layer, moving through the hidden layers, and arriving at the output layer. An artificial neural network simply chains basic mathematical transformations together. Every intersecting line between these nodes represents a unique parameter, a weight that the algorithm must optimize. To train a structure this complex, the system relies on a mathematical technique implemented in the 1970s called backpropagation. Backpropagation processes the error rate at the output layer and distributes that error signal backward through the system, updating the weights in reverse. This backward flow allows the system to simultaneously tweak millions of parameters across all hidden layers to drive the final output error down to its minimum. While backpropagation was mathematically sound decades ago, it remained dormant. The sequential CPUs of the era were incapable of calculating millions of simultaneous error updates. This architectural comparison illustrates the hardware transition that catalyzed the 2009 deep learning boom, the graphics processing unit. A CPU sequentially processes a few data blocks one at a time. A GPU processes hundreds of operations simultaneously in parallel. Originally designed to rapidly render millions of pixels for the gaming industry, the GPU provided the parallel processing architecture required for deep neural network training. Model capacity exploded. Networks scaled from thousands to billions, unlocking modern computer vision, speech transcription, and generative text. But this immense scale introduced a trade-off, the inverse relationship between a model's predictive capability and its human interpretability. We could easily verify the 2-parameter linear regression model, but a multi-billion parameter neural network is an opaque black box. Data scientists cannot fully map how it weighs every single input to arrive at an output. Because humans cannot manually audit millions of internal parameters, unrepresentative or biased training data will mathematically guarantee biased predictions in production. Machine learning is not cognitive intelligence. It is a mechanical assumption that the future will perfectly mirror the past. If the historical data is flawed, the algorithm will flawlessly optimize for the wrong rules.